And now for something completely different. I worked with the organizers of this conference for more than a year to talk about how to do international conferences and to feature English language prominently, as is important to do. It wasn't my idea, but it's important to do it, as you know. And I thought I had nothing to offer as far as a contribution to the conference because I'm a historian. I taught European history for a long time. I retired recently, and I spend a lot of time working on international education, on organizations that do international meetings. And of course, I've been doing most of my writing has been editing the work by colleagues, most of them from Ukraine and Russia and recently Brazil, to help them to publish in English with a higher standard and to understand the publication norms of Western journals. So this is what I'm offering to you as a contact for something like that. And what I can offer to you is to listen to me speak in my native language, which you don't always hear English spoken by a native speaker. So maybe that's important. But Docent Karpiuk convinced me that I did know something of interest to you. My own history was I was a student of chemistry when I began, and then changed to history of science. Our education is rather different in the United States in that if you're a chemistry student, you must take courses in English and psychology, and for chemistry, you must take courses in mathematics and physics. You must take a lot of them in those departments, not in your own department. And my first course in physics was given by this man named E.M. Purcell, Edwin Purcell. We called him Electromagnetic Purcell, E.M. Purcell. And it turned out he was famous, old gentleman, famous for, I say discovering NMR, but he didn't discover it, he developed it. He developed it in precisely the way that it's interesting for you. And I'll tell you that story because it's interesting. So there you see the picture of Purcell about the time that he did the work on and that won the Nobel Prize. And there you see from his Nobel Prize lecture something of interest to you. He said, we can do this with NMR. And I don't know if you can tell the molecule there, it's ethanol. And ethanol has, the important thing about NMR is the hydrogen nucleus, the proton, and it gives you the structure of the atom of the whole molecule by knowing where the hydrogens are. There are three different kinds of hydrogens on this ethanol molecule, and so you get three different peaks. And this was the earliest one published, as far as I know. You should see that there's something wrong with this picture. I'll let you think about what that might be. Now I'll tell you about my teacher. He was born like me, in the Middle West. I was born right here in southern Indiana, and about, 40 years, 50 years before I was born, Purcell was born here in the middle of Illinois. I was born on a farm. He was born in a small town where his father worked for the telephone company. And so young Purcell had a lot of electrical equipment and wires and magnets and bells, and also the publications of Bell Laboratories, which was the most really famous electrical engineering company in the United States when he was a child. And so it was natural that he would want to do what I wanted to do, was to go to Purdue University right here I wanted to go because I wanted to study chemistry. He wanted to go because he wanted to study electrical engineering. It's a place for engineers and agriculture. Now, when Purcell went, it was not a great science school. It was a school for engineering. But bad things were happening in Europe. And a lot of Jews, especially, were leaving Europe and leaving the great universities to come and work in America. And for some reason, they hired in electrical engineering what Purcell called a real physicist, a young man from Austria who recognized in Purcell not an engineer, but a scientist. And so he urged him to get an opportunity to study in Nazi Germany, to study with great physicists there, 1 year, and then to get a scholarship to go to Harvard, where he could learn real physics. And so he did, and he got his PhD in 1937. Of course, that's getting closer to the bad times. He taught physics, and because he knew electrical engineering very well, they put him to work on a Harvard cyclotron. And I think you may know from physics, a cyclotron, also called atom smasher, is a way of accelerating charged particles in electrical and bending them in a magnetic field so they have very high energies. And they were used really, this technology was used to develop, it was invented in Berkeley, and it was used to develop nuclear energy and understanding of nuclear properties. So Harvard had to have one too. They built one in the Soviet Union, they eventually built one in Germany as well. And there is young Purcell taking care of the, you can recognize his face, taking care of the magnet. It's a huge magnet. You know, here's part of it here, here's part of it there. And then there's electronics inside and things that make the cyclotron. But the biggest thing is the magnet. So he had this, the biggest magnets in the world, strongest magnets in the world in cyclotrons in those days. So this was his experience. And then the war began. What happened to these young physicists during the war is, well, the story is that America, United States, really becomes the center of scientific research in this period. Why? Because so many good physicists, Einstein, just one of them, come from Europe to America. Some go to England too. But England was in the war, and England was being bombed by the Nazis, almost to nothing. And the important weapon against the Nazis was going to be radar. Everybody had radar. The Nazis had radar, and the English had radar. But the English were developing better radar. For example, you could bounce radio waves off the ionosphere, and you could see something coming that was beyond the horizon. But think about that. Radio waves, the ionosphere, and then back, and then read the signal. What kind of signal? And you know what radio is like. Static. Everything produces radio waves. How do you filter out the signal that you want? These are the problems that they solved in what they called the radiation laboratory at MIT. MIT was just up the road from Harvard. Oh, by the way, where is Harvard? Purcell went there as a graduate student, and I went there as an undergraduate student and studied with Purcell. Okay, so if you could make a radar and put it on an airplane, it would be great, because then you could be up high and you could see much further. So that was their job at MIT, and Purcell had to go up the street to MIT and work there. Top secret. Even the European scientists could not work at this laboratory. They didn't have security clearance. Even more secret was what they were doing at Harvard, which was called the Radio Research Lab. Nobody knew what they were doing there. They were trying to do radar jamming, so that radar could not work, for the enemy. And the old radiation lab was at Berkeley. They were working on something that people thought would never work, the atomic bomb. So there was these three projects. In the beginning, in 1940, nobody thought the atomic bomb would work, so you let anybody work on that. It didn't matter. It almost didn't finish by the war anyway. But radar did. They worked on the over-the-horizon radar and worked out problems of signal to noise in radio detection. That is, get out the noise, get the signal, and get very high resolution of these signals. And they finally got radar, a little help from the Soviet Union actually in getting the airborne radar. You have to get more energetic waves that almost become microwaves to make a small radar to put on an airplane. But once you do that, you can detect airplanes, you can detect targets in bad weather, you can detect submarines, and the United States and Britain had this weapon. The Nazis did not have it, not for a long time. But you had to develop good technology, and at these higher energies, which means smaller wavelength, something around 10 centimeters. Here's the electromagnetic spectrum. We see here these colors just in that one little bit. There are lots of radio waves, something over a meter, sometimes many meters in their wavelength, low energy. And as you get shorter into centimeters, you're in the realm of microwaves. If you have too many microwaves, it's like cooking in your microwave oven, right? But they couldn't do that because they didn't know how to make and control microwaves and small radar waves. A Soviet scientist developed this magnetron, and the English perfected it, and that's how they made the short radio waves and the microwaves for these first machines. Later they replaced it with a klystron tube, and that's how you cook, how you warm your coffee in the morning with that microwave. So the spectrum, electromagnetic radiation, what did they do? Well, how does nuclear magnetic resonance figure here? Well, there I have to do some hand-waving physics, very complicated physics very quickly. We are lucky that there is quantum mechanics, even though it's very hard to understand and hard to study. We're lucky because it gives us spectroscopy and spectra. Not continuous, but definite spectra. For example, they long knew that there were absorption and emission lines in the spectra, but they didn't know why. But after the discovery of quantum mechanics by mathematics and physics, they found out that only certain electron orbitals are allowed, and then when the energy is absorbed or the energy is lost, you get exactly that energy, that wavelength in the spectrum. Nothing else, just that. Okay, that's the first thing you have to know. Electrons have a lot of energy. They're going very fast. The proton of a hydrogen atom is sitting there. It probably does nothing, but that turned out not to be true. Putting together quantum mechanics and relativity, it was discovered for protons and then for all atomic particles that they spin. And the spin numbers is what gives you the possibility of nuclear magnetic resonance in some nuclei. Only a few. It's very lucky that hydrogen is one that you have it. They knew that nuclei spin because Pauli and Sommerfeld worked out the theory, and then Stern and Gerlach proved that the either north-facing or south-facing magnetic poles would split under a big magnet. So the Stern-Gerlach experiment said, yes, silver ions whizzing past have nuclear momentum, have magnetic momentum. And then comes Isidore Rabi. This is the man who really discovered nuclear magnetic resonance, but he did it in molecular beams, first in lithium ions. He bent them one way and then the other, at the same time applying radio waves, because they worked out exactly what the frequencies should be. They knew that from quantum mechanics. And then he got the absorption line from those radio waves, exactly to show that the momentum would take a higher energy and spin faster, let's say, if you get exactly that thing. How are you going to use this information? Well, you use it to determine exactly what are the magnetic moments of certain things. And hydrogen turned out to be an easy thing to calculate and then to measure to prove the calculation. Later, notice the year, he got the Nobel Prize for this. I'll mention that in a minute. By the way, Robbie is almost a countryman of yours. He was born near Lviv, just on the other side of the Polish border in Austria in those days. His family fled persecution of Jews. He grew up in New York City. He was a good science student. They sent him to Germany, and he studied the good physics, and then he left Germany to come back to New York when the Nazis took over. And this is the story of American greatness in science, these European physicists. Robbie was also the director of the group that Purcell worked with at MIT. And it was about radio waves, radio detection, controlling radio microwaves in these systems. They finished the project, and then they talked about physics. And this is what Purcell thought of and another young man thought of. Now, the other young man was working at Harvard, and he got to visit with Robbie, but Purcell could not go to Harvard. He was not allowed to go there. That was too secret. So the two of them worked on the same problem, and it turned out they had the same discovery almost at the same time, and they both got the Nobel Prize. What makes NMR possible is because hydrogen atoms and a few other atoms have a net spin. Most things don't. They fill up, net is zero. Magnetic momentum that you could measure would be zero. But hydrogen has 1/2 plus, 1/2 minus, but they're in all directions. How could you get them lined up so that you could hit them with a probing radio wave and get them to resonate, get to a higher energy, and then to emit a radio wave that would be characteristic of the hydrogen atom? Well, you have to line them up in a big magnet. And where do you have such magnets? From nuclear research, from cyclotrons, from cosmic ray research. Harvard had a couple of them, and Stanford had one. And so after the war was over, these two young men went back to their laboratories, put together their theory and their knowledge of radio and their big magnets that were just sitting around doing nothing at that point. And they both basically put together the first liquid and solid state NMR. Not magnetic beams, but a sample that you can put in a tube between the magnets. You line up all the magnetic momentum of the hydrogen atoms, and then you put in with that graviton the exact radio wave that you need. You excite them to the higher state, you turn that off, let it relax, it will emit a signal, and that will show you, well, resonance, nuclear resonance, which would not be very interesting when they first discovered it. It just proves something. Not interesting for chemistry. Why? Because if you do water, like one of them did, how many different kinds of hydrogen atoms do you have in water? One. They're all symmetrical. Even if you line them up and you get one big peak. But, as I showed you at first, he found that with ethanol, we know this structure, it's a simple one. There are actually 3 different kinds of hydrogens, because what happens, there's a chemical shift that occurs because even though all the hydrogens resonate at the same energy, when they relax, some of them are shielded by the bonds. And the bonds are 3 different kinds. Bonds between hydrogen and carbon, bonds between hydrogen and carbon that are next to oxygen, and the hydrogen bond on the oxygen that is a very special kind of bond. So Purcell and his group worked on this part. Higher resolution, shielding, and developing a standard Trimethylsilane worked out very good, the so-called TMS. They usually make 0, and then they do parts per million away from 0. And there you get the, should be more familiar NMR spectrum of ethanol. And remember I told you that Purcell had put it in backwards. Well, you know, when you're doing a graph, backwards is as good as forwards, but eventually you develop a standard. So he had this worked out from the time of late 1945, when they first proved the experiment. He did it with paraffin, which was almost the same as water, 1 peak. But then when he published in 1952 his Nobel lecture, he put this in, and he said he was working with his assistant, a young Dutchman, not Jewish as it turned out, but he left Holland because everything was destroyed. He came to Harvard and worked with Purcell and did the work for nuclear magnetic resonance and all the, well, they learned, for example, about near neighbors and splitting. You split the peaks. Or that you could even use some other things besides hydrogen, carbon-13, to get magnetic momentum there too, to learn more about the structure. What NMR gives you that no other spectroscopy gives you is the structure of the even very complicated molecule like this one, which actually transposes into different ones and will give you different peaks from both kinds of things. It can get very, very complicated, but the first thing is to have all the technology together. And also to understand the very profound quantum mechanical, relativistic, all those things had to be together. Plus, you had to have a big fat magnet that cost many thousands of dollars. Well, Bloembergen went on to win a Nobel Prize for laser spectroscopy and doing entirely different things. Purcell almost won another Nobel Prize because he discovered hydrogen 21 centimeter line in the universe, hydrogen atoms kind of dispersed through the universe. That was important for them. But they both shared the Nobel Prize in '52. Bloch had gone back to Stanford. He had done the water. Purcell had was back working at Harvard. He had done paraffin, but then later with Bloembergen worked out the kind of NMR spectroscopy that you do. And it was for the development of new methods of nuclear magnetic precision measurements and discoveries in connection therewith. They shared that prize. Afterwards, now today, you can get smaller equipment, and electronics, of course, is much better and can be cheaper. But the one thing that can't be cheaper are these huge magnets that have to be of the order of 1 Tesla, or old measurement 10,000 Gauss. So you might be able to find a simple machine for $100,000. You probably need one for your research, something about $500,000 or $1 million, a good NMR spectrum. But this technology in the 1980s expanded when they took the basic principle and made it into a kind of sweeping medical measurement. And it was first called nuclear magnetic resonance imaging, but because they were putting people into these machines to see where cancers and bleeding and other things are, they dropped the nuclear because people thought that there was radioactivity in it. There's not. The nuclei are just hydrogen atoms, right? That's the nucleus. They call it MRI imaging. These are big machines that cost millions of dollars, and they can look inside people without x-rays and harmlessly to detect things internally. This is Purcell that I knew, a beloved teacher of physics, a great writer in science, someone who cared. This is a basic but difficult textbook that they still use today, that he authored all by himself to explain electricity and magnetism. There's the 2 articles that got him the Nobel Prize. There's the one about the 21 centimeter spectrum in the universe. There's his textbook that I used, and there, when he died, his biography. So I hope the hand waving was not too upsetting. If there's something I can explain for you, please ask me a question. I'll try. And otherwise, I thank you very much.